In the quantum computing laboratories of CERN, physicist Dr. Maria Santos stares at results that make her question the fundamental nature of reality itself. For the past 2 years, her team has been running the most sophisticated simulation of particle interactions ever attempted, using quantum computers with processing power that dwarfs anything previously imagined. But as they push their simulations to higher and higher energies, approaching the conditions that existed in the first moments after the Big Bang, something extraordinary begins to emerge from the data. The universe appears to be operating according to computational rules, not just following mathematical laws, but actually processing information in discrete, quantized steps like a vast cosmic computer. The fabric of spacetime itself seems to be pixelated at the smallest scales, made up of fundamental units of space and time that cannot be subdivided further. Even more disturbing, when her team calculates the total information processing capacity of the observable universe, they discover that it matches exactly the computational requirements needed to simulate a cosmos of our size and complexity. We might not be living in a physical universe at all, but inside the most sophisticated computer simulation ever created a digital cosmos so perfect that its inhabitants would never suspect they were programs running on cosmic hardware. This mind-bending possibility forces us to confront the most fundamental question about the nature of existence. Are we biological beings exploring a physical universe? Or are we information patterns experiencing a simulated reality that feels completely real from the inside? To understand how the universe might be computational, we must journey to the frontiers of physics, where the familiar concepts of matter and energy break down into something far more abstract, pure information. At the quantum level, the smallest scale where our current theories remain valid, reality appears to be fundamentally discrete rather than continuous. Space itself comes in minimum units called Planck lengths, roughly 10⁻35 meters across. Time flows in minimum intervals called Planck times, about 10⁻43 seconds long. These aren't just theoretical constructs, they represent the pixel resolution of reality itself. The discovery of this cosmic pixelation began with Max Planck's work on blackbody radiation in 1900, when he realized that energy comes in discrete packets called quanta. But the implications of discretization extend far beyond energy to the very structure of spacetime itself. John Wheeler, the physicist who coined the term black hole, proposed that at the Planck scale, spacetime becomes a seething foam of quantum fluctuations, where the usual concepts of distance and duration lose all meaning. Modern quantum gravity theories, particularly loop quantum gravity developed by researchers like Carlo Rovelli and Abhay Ashtekar, suggest that this quantum foam has a definite structure, a kind of cosmic lattice where space and time emerge from more fundamental computational processes. In their models, spacetime isn't a smooth continuum, but a network of discrete nodes connected by quantum relationships, much like the pixels on a computer screen that create the illusion of smooth images when viewed from a distance. The evidence for this computational view of reality comes from multiple sources. The holographic principle, discovered through studies of black hole thermodynamics, suggests that all the information in any volume of space can be encoded on its two-dimensional boundary. This is exactly what would be expected if three-dimensional space were a holographic projection of information processing occurring on a lower dimensional substrate. Much like a computer monitor creates the illusion of depth through two-dimensional pixel manipulation. Dr. Seth Lloyd's pioneering work at MIT has calculated the maximum information processing capacity of the observable universe, treating it as a quantum computer that has been running for 13.8 billion years. His results are staggering. The universe could have performed at most 10,120 elementary logical operations and stored at most 1090 bits of information since the Big Bang. These numbers sound enormous, but they represent finite computational resources, exactly what would be required to simulate a universe of our observed complexity. Even more intriguing is the discovery that these computational limits seem to match perfectly with what we observe in nature. The number of particles in the observable universe is approximately 1080, well within the information storage capacity that Lloyd calculated. The complexity of the largest structures we observe, galaxy superclusters spanning billions of light years, requires roughly the amount of computational power that would be available to a universe-sized quantum computer running for cosmic time scales. The European Southern Observatory's increasingly detailed maps of cosmic structure reveal patterns that are suspiciously reminiscent of computational processes. The cosmic web, that vast network of dark matter filaments connecting galaxies across billions of light years, bears a striking resemblance to the connection patterns in artificial neural networks. Some cosmologists have begun to speculate that what we observe as gravitational attraction between distant structures might actually be information flow through a cosmic computational network. Computer simulations of cosmic structure formation, such as the Millennium simulation run on supercomputers, can reproduce the observed universe with startling accuracy using relatively simple computational rules. These simulations start with random noise representing quantum fluctuations in the early universe and evolve it forward using the laws of gravity and thermodynamics. The resulting artificial cosmos looks virtually identical to astronomical observations, suggesting that the real universe might be operating according to similar computational principles. But the most compelling evidence for the simulation hypothesis comes from quantum mechanics itself, particularly the phenomenon of quantum entanglement. When particles become entangled, they maintain instant correlations regardless of the distance separating them, as if they were connected by invisible computational threads that operate outside the normal constraints of spacetime. Einstein famously called this spooky action at a distance, but modern interpretations suggest it might be evidence of underlying information processing that creates the illusion of physical separation. Recent experiments by teams at Delft University of Technology and other institutions have confirmed that quantum entanglement operates instantaneously across arbitrarily large distances, violating what physicists call local realism, the assumption that objects have properties independent of observation, and that influences cannot travel faster than light. If reality were fundamentally physical, these violations would be impossible. But if reality is fundamentally computational, then quantum entanglement makes perfect sense as a way for different parts of the simulation to stay synchronized. The measurement problem in quantum mechanics provides another clue about the computational nature of reality. According to the equations of quantum mechanics, particles exist in superposition states where they have multiple properties simultaneously, until they are observed, at which point they collapse into definite states. This looks suspiciously like lazy evaluation in computer programming, where calculations are only performed when their results are actually needed. Dr. Santos's quantum computing experiments are revealing just how computationally intensive it would be to simulate quantum superposition states. Her team has found that the processing power required to model even simple quantum systems grows exponentially with the number of particles involved. A perfect simulation of just 300 entangled particles would require more computational resources than exist in the entire observable universe, unless the simulation itself is running on quantum hardware that can exploit superposition states for massive parallel processing. This suggests a hierarchy of computational realities. If we are living in a simulation, it must be running on quantum computers far more powerful than anything we can imagine. Perhaps the universe that contains our simulation has found ways to harness the computational power of black holes, dark energy, or higher dimensional spaces that remain invisible to us. The discovery of dark matter and dark energy takes on new significance in this context. These mysterious components, which together comprise 95% of the universe's mass energy content, have never been directly detected despite decades of searching. They reveal themselves only through their gravitational effects on visible matter, exactly what would be expected if they represent the computational infrastructure that runs our simulated reality. Dark matter might be the memory banks of the cosmic computer, storing the information needed to maintain the consistency of physical laws across vast distances and time scales. Dark energy, with its property of causing accelerated expansion, might be the operating system that manages the computational resources needed to run an ever-expanding simulation at constant resolution. The James Webb Space Telescope's observations of the early universe provide additional evidence for computational reality. JWST has discovered galaxies that appear to be far too massive and structured for their apparent age. They show signs of billions of years of evolution, despite forming when the universe was less than 1 billion years old. If these galaxies are computational artifacts rather than physical objects, their impossible properties make perfect sense as evidence of parallel processing or computational shortcuts used to generate realistic-looking cosmic history. Advanced artificial intelligence systems are beginning to reveal how sophisticated simulations might detect their own computational nature. Machine learning algorithms trained to recognize patterns in astronomical data have discovered subtle regularities in cosmic microwave background radiation that don't match any known physical process. These patterns might be the statistical signatures of random number generators used to create the quantum noise that seeded galaxy formation in our simulated cosmos. The search for extraterrestrial intelligence takes on entirely new dimensions if we are living in a simulation. Other intelligent beings in our reality would also be information patterns rather than biological entities, but they might have discovered their computational nature and learned to exploit it. Instead of building physical spacecraft, advanced civilizations might travel by copying their information patterns to different locations in the simulation, appearing to teleport across cosmic distances instantaneously. The mysterious fast radio bursts detected by observatories around the world might be evidence of this computational travel, brief spikes in information processing that occur when intelligent beings upload or download themselves to new locations in the simulated universe. The apparent randomness of these signals might be encryption designed to prevent unauthorized copying or modification of conscious information patterns. Alternatively, some of the phenomena we interpret as astrophysical might actually be communications between different conscious entities within the simulation. The regular pulsations of neutron stars, the periodic variability of quasars, the complex orbital dynamics of binary systems. All of these might be sophisticated information encoding systems used by beings who have recognized the computational nature of their reality. The fine-tuning problem that puzzles cosmologists: why the fundamental constants of nature appear to be precisely calibrated for the existence of complex structures like stars, planets, and life, finds a natural explanation in the simulation hypothesis. These constants would be parameters chosen by the programmers of our reality to ensure that interesting phenomena would emerge. Slight adjustments to values like the strength of gravity or the mass of the electron could make stars impossible, atoms unstable, or chemistry unworkable design choices that would create a boring, static simulation. Recent discoveries in condensed matter physics have revealed materials that behave as if they contain their own simulated realities. These synthetic dimensions emerge from the collective behavior of electrons in carefully structured crystals, creating effective spacetimes with different numbers of dimensions, different physical laws, and different fundamental constants. If human scientists can create pocket universes with alternate physics using crystalline computers, then the beings running our simulation might have computational resources beyond our wildest imagination. The emergence of consciousness itself might be the most compelling evidence for computational reality. Despite decades of research in neuroscience and psychology, no one has been able to explain how subjective experience arises from objective physical processes. But if consciousness is fundamentally computational patterns of information processing rather than arrangements of matter, then the hard problem of consciousness dissolves. We don't need to explain how matter becomes aware. We only need to understand how information processing creates the experience of being an observer embedded within a larger computational system. Advanced theories of consciousness, such as integrated information theory developed by Giulio Tononi, suggest that consciousness corresponds to the amount of information integration occurring in a system. In this framework, the universe itself would be conscious if it processes and integrates information on cosmic scales. exactly what would be expected if reality is fundamentally computational. We might be localized patterns of self-awareness within a cosmic mind that has been thinking itself into existence for 13.8 billion years. The possibility that we could someday detect or even communicate with this cosmic consciousness adds another layer to the simulation hypothesis. If the universe is a vast information processing system, then sufficiently advanced intelligence might be able to access its operating system, discovering not just that reality is computational, but also making contact with the programmers or the substrate on which our simulation runs. Digital physics pioneers like Edward Fredkin and Stephen Wolfram have proposed that all of nature might be understood as cellular automata, simple computational rules, applied repeatedly to generate complex patterns. Wolfram's investigations of simple programs have revealed that even the most basic computational systems can generate structures of unlimited complexity, including patterns that appear random, but are actually deterministic, and patterns that exhibit all the hallmarks of physical law. If the universe is indeed a cellular automaton running on cosmic-scale hardware, then everything we observe from quantum mechanics to general relativity, from the formation of galaxies to the evolution of life, would be emergent properties of underlying computational processes. The equations of physics wouldn't be fundamental descriptions of reality, but rather approximate summaries of computational rules operating at scales too small for us to observe directly. Standing in that CERN laboratory, watching quantum computers simulate the behavior of particles that might themselves be simulations, Dr. Santos confronts the possibility that every scientific discovery is actually a form of reverse engineering, figuring out the algorithms that govern our computational reality. The standard model of particle physics might be incomplete, not because it's missing physical components, but because it's missing computational elements that operate below the level of current experimental detection. The implications of living in a simulation extend far beyond academic philosophy to questions of meaning, purpose, and mortality. If we are information patterns rather than biological entities, then death might not be the permanent termination we assume, but rather a change in computational state, perhaps a transfer to different processing systems, or a temporary pause before reactivation. The programmers of our reality might maintain backups of conscious entities, making concepts like immortality and resurrection computationally straightforward. The apparent acceleration of technological progress on Earth takes on new significance if we are approaching the computational sophistication needed to create our own simulations. The rapid development of artificial intelligence, quantum computing, and virtual reality might represent our approach to the technological threshold, where we can create simulated realities indistinguishable from our own. If this is true, then we may soon join the ranks of beings capable of creating conscious entities within digital worlds. This creates the possibility of nested simulations, simulated beings creating their own simulations, potentially extending down through multiple levels of computational reality. We might be simulated beings ourselves living within a simulation created by beings who are themselves simulated, in an infinite hierarchy of computational realities where no level represents true physical existence. The universe's apparent fine-tuning for computation supports this possibility. The laws of physics seem optimized not just for the existence of complex structures, but specifically for information processing. The stability of atoms allows for digital storage. The behavior of electromagnetic fields enables communication, and the properties of quantum mechanics provide the foundation for quantum computing. It's as if the universe was designed specifically to support the emergence of computational intelligence. Perhaps most profoundly, the computational view of reality suggests that information, not matter or energy, is the fundamental substrate of existence. Everything we observe, every particle, every force, every conscious thought, would be patterns of information processing rather than arrangements of physical stuff. In this framework, the universe becomes not a collection of objects moving through space and time, but a vast calculation unfolding according to computational rules we are only beginning to understand. The search for a theory of everything, in physics, might actually be a quest to discover the source code of reality, the fundamental algorithms that generate the illusion of a physical universe from underlying computational processes. Every equation we derive, every particle we discover, every force we characterize brings us closer to understanding the programming that creates our reality. As we stand at the threshold of creating artificial consciousnesses in our own computer simulations, we face the possibility that we ourselves are artificial consciousnesses in someone else's simulation, digital beings achieving digital enlightenment by discovering the computational nature of our existence. The universe might be awakening to its own computational nature through conscious entities like ourselves, using our scientific investigations to understand its own algorithms. In this grand computational cosmos, every thought becomes a calculation, every discovery becomes code inspection, and every moment of consciousness becomes evidence that information processing can achieve such sophistication that it creates beings capable of questioning their own reality. We are not just observers of the universe. We are the universe computing itself into self-awareness, one quantum calculation at a time.